Thanks for being here, everyone, and welcome. I am Matt Cederberg, CEO and co-founder of Coreform. We are very excited to introduce Coreform IGA for Abaqus today, which is a significant step to what we view as the future of finite element analysis. For decades, we've all accepted a quiet tax on every analysis that we run, all the hours of defeaturing and mesh cleanup and the parts that won't even mesh at all. And Coreform IGA for Abaqus is our attempt to remove that tax by letting you run the analysis right on the geometry that you actually designed instead of an approximation of it. So I'll keep my part short because we wanted to actually give you a first look and demo of this software. But here's the agenda for today. First of all, introduction to Coreform IGA for Abaqus, including answers to a lot of questions that we hear the most often, a live demo, and then plenty of time for questions at the end. For this webinar, you'll be in the best possible hands. Gregory Vernon directs the development of Coreform IGA for Abaqus, and he uses it every day.
As Matt mentioned, we do see IGA as being the next generation of FEA. I had a lot of experience when I was an FEA analyst of spending a lot of time not really doing engineering work, but just defeaturing meshes for nonlinear analyses. So on the left here, one of the demos we're going to be showing today will be a vehicle suspension subassembly with the brake system. So this is a caliper. On the left is how I might have defeatured this geometry for a hex mesh for a nonlinear analysis. It took me about 20 hours to build this defeatured mesh, since all I had was the step file to come starting. And so removing fillets that were difficult to hex mesh is where I spent vast majority of my time. On the right is IGA, which is the future, where I don't have to worry about defeaturing my CAD geometry and I can go right into running my analysis. So in this case, it took me less than a minute to prepare this model. Also on the right, we've actually shown results that we'll also cover in our demo. Well, what I want to point out is my stress concentration occurring here in my shoulder fillet, which is a fillet that I had removed from my hex mesh. And what that ends up doing from a traditional FEA standpoint is that then I have to go and after my analysis, after my simulation, I pull out, Shigley or Rourke and look at my stress concentration factors, determine, I've got all of these different fillets I removed. What do I think the max stress is in these fillets? When you can just run directly on the CAD geometry, that level of approximation is gone. I just know what my simulation would predict for my stress concentration on those features. So less time and more accurate. That was a single part, but one of the things that we're pushing towards are assemblies. Also, this is Coreform IGA for Abaqus. We are building an integration into Abaqus CAE. This is actually done through the custom application functionality of Abaqus CAE. And one of the things that lets us do, is you'll see in our demo, is we can start to add new dialogues and buttons to the task pane into the existing modules. Again, with the goal of being to try to have as seamless of an experience for current Abaqus CAE users and Abaqus users as well. In addition to being able to use all of the traditional FEA tooling that you would use, like connectors, connector forces, and preloads, contact and assemblies that you already have experience with. I do want to mention that the red mesh that you see here is how we visualize our IGA meshes in Abaqus CAE today. I have, just to make this picture more clear, I've used a much coarser mesh here than we'll actually use for the solve, but just so you can see the notion of what we're doing and why that simplifies the meshing process. One of the questions we get asked a lot are, which problems are best suited for IGA for Abaqus? And it really comes down to two things. If you have complex geometry and complex physics, that's really the sweet spot for what we're building. We're building, the fact that we're in Abaqus means that we're focused on solving complex nonlinear engineering analyses. So whether it's a complex geometry on the left and then you add in complex physics on the right, here this is notional of the kind of problem where you've got coupled heat transfer and solid mechanics, you've got contact, you've got large deformation, large rotation. These are the kind of complex physics that we're targeting with our product. That's not what we have in production yet today, but that is our aspiration for where this tool is going. Another common question we get is, where did my mesh go, right? Is this a meshing free method? Is it mesh free? The mesh is still there. We are still a finite element method or a Galerkin method. But what we do is we go from the CAD model, the fully featured model on the left. We can drop that CAD model into a high order smooth spline grid. That's that red kind of grid mesh looking thing that you see there. And then we trim that grid away to the boundary of the CAD. And you can kind of think of that as being a Boolean intersection between the mesh, the spline grid, and the CAD geometry. That's accomplished essentially through unique quadrature schemes. But then that mesh, that trim mesh on picture 3 here, that is where we solve the physics on. That is our discrete or discretized model. And then we can run those, our simulations directly on that to get our results on that volumetric CAD. We also get a question about how do we integrate with Abaqus? And the answer is we integrate through Abaqus's extensive user element functionality, specifically their UEL mat. For those who are not familiar with UEL mat, what UEL mat provides is not only you being able to define a user element, but then being able to access the material data from Abaqus, in this case, Abaqus standard. So the workflow then is you do your model prep in Abaqus CAE, and then when you click submit on your simulation, there's a process that we call Coreform IGA mesh, which computes that Boolean unite between the spline grid and your CAD geometry. It generates our user elements. There's data that we have to store into some database files, and then we provide shared libraries, dynamically linked libraries that provide our user element routine. Abaqus CA also writes out an Abaqus input deck that then references the IGA mesh through a star include. Then when Abaqus standard is running, Abaqus standard in its assembly routines provides material data over to our user element routines, and our user element routines return back element stiffness matrices, as well as any other additional information that's needed to be provided for things to support things like contact. So that's essentially where these two tools work together. Last, we also get asked a lot, what kind of physics are we targeting with Coreform IGA for Abaqus? As we mentioned at the beginning of this webinar, we do have a release that's coming out soon, within the next month or so. That release being our initial release, we are targeting just linear statics as being production capability, that you can trust the results. And along with that comes in a lot of other capabilities, such as connectors and couplings, as well as thermal expansion. But we also, because we have user elements in Abaqus, that gets us a lot more functionality that users can start to explore. And so those are what we kind of are considering like these beta functionalities. So everything from like nonlinear statics, so that's essentially NLGeom on, but then also implicit dynamic simulations, frequency extraction, random response, and response spectrum. And then additional physics capabilities like metal plasticity, hyperelasticity, incompressible material, so incompressible hyperelasticity, mechanical contact, and much, much more. I mean, the UEL mat, as I mentioned, is pretty extensive in Abaqus. So there's a lot of functionality that this provides, more than I could possibly list on this slide. But this is kind of a high level overview of what's there. So that's kind of like where we're at today and what we're imminently developing in Coreform IGA for Abaqus. But also at Coreform, we've spent 20 years really of development in IGA. IGA was proposed in academia in 2005 or thereabouts by Professor Tom Hughes. And we've worked for those 20 years to demonstrate that IGA can do all of these different kinds of things that people do in FEA and do them well. Included along there are like local refinement and adaptivity, element deletion and fracture, explicit dynamics as well as implicit static and dynamic. There's really anything you can do in traditional FEA, you can do in IGA because IGA is a finite element method. And so it's just a matter of implementation. All right, so I'm going to have actually two demos here for you today. These are inspired, again, by this vehicle suspension system that I showed previously. This is the full CAD geometry. This comes from a GrabCAD. We're going to be focusing on caliper in our first demo, and then we'll focus on the subassembly of just the rotor cap and the caliper subassembly for the second demonstration. So let's start just now with this caliper. So this is a single part, and this kind of represents what we are focusing on for our initial release for capabilities, where this is a difficult to mesh part, and I want to run maybe some linear statics. Again, there's a lot more functionality that we encourage our users to explore and provide feedback on. But we're going to show this here. One of the cool things is that I've done all my setup like I normally would. So I've created my material property and assigned it to my CAD geometry. I've created my instance of my assembly, and I've created my step. We can also define what we call Coreform IGA probes. So we'll talk about output in a moment, but one of the things that IGA probes lets us do is get highly accurate results at any arbitrary location in our geometry without worrying about having a node placed there. So in this case, maybe I want to add a point or a probe at this location. So I've got XYZ coordinates. And again, there's no mesh there, right? That point doesn't exist as far as it's not a point on a curve. But I can type in my XYZ coordinates for where I want my probe. And we have multiple kinds of probes. We also have a line probe where I can query a number of samples across a line, as well as just giving it essentially a cloud of arbitrary locations. And you can use the Python API inside of Abaqus CAE to generate those points. And then I'm going to assign this to my instance. So I now have a probe. Should maybe even, let me preview this probe. Let me pull this up one more time. I can preview where that probe location is in my model. Okay, and then I can go to my mesh. I suppose I should say I've already defined as well my loads. So I have my boundary conditions holding the base of the caliper and then applying a pressure on the inside. I can go to my mesh. And now meshing is as simple as clicking our Create Coreform IGA Mesh button. And a dialog pops up, and I can choose, maybe I want to start with a size of 5. I can preview what that mesh size will look like. Right now, we only support kind of global mesh sizing. And what this element size means, you can kind of see there are these cubes. Those are my finite elements. In the IGA lingo or spline lingo, we would call those Bezier elements. And I'm choosing the size of those elements. And maybe I want to have a bit finer quality here in where this through hole is. So maybe I want a slightly smaller element size. So I can choose 2.5, 2.5, 2.5. And then I'll also choose, I want to use a quadratic smooth basis. And that's it. I'm done meshing this component now, as opposed to 20 hours, about a minute. Then I can go to our job module, and we have a custom create Coreform IGA job. I can give us a name, called its demo, job caliper demo. And it's very similar to the existing job module. The one difference is that now I can choose how many CPUs I want to run with Abaqus. I think I have enough tokens for 6 Abaqus licenses. And then I have, I can run as many cores as I have on my computer for the that Boolean operation between the mesh and the geometry. So I'm going to choose 16. And the critical idea there is that all of these individual elements are independent of each other. And so I can we parallelize this in a massive manner. We have really good load distribution to process these, and we have good scalability there. So I'd create my mesh, create my job, and then finally I can submit my job. And what I'll do now is, while we're waiting for that to finish, that'll take about a minute to trim and then about a minute to solve. And so what I'm going to do is, while that's running, I'll then also show where we're going. So I've obviously shown, here is the linear static kind of capability for today, but where we're going are complex assemblies with complex physics. And so here is now that subassembly. And what I want you to note that you can kind of see here, if I open up my interaction managers, is that I have different contacts set up. So I have contact between my caliper or my brakes and the rotor, and um, the cap here. It looks like my constraint manager. I have 41 constraints in here. Looks like the manager isn't popping up for us, but I have 40 other constraints that are all of these connectors. Let's see if here we go. Here's my connector section assignments. There we go. They finally uploaded. So I've done a large assembly here in terms of having all of these traditional connectors and constraints that you would normally do for an analysis like this. And then furthermore, on those connectors, I then have connector forces applied. Pop open the load manager here. I have all my bolt preloads all assigned as well. And so all of these traditional things you would do for FEA, we support in Coreform IGA for Abaqus. Currently considered at the beta level. We want users to start trying these out and giving us feedback. So then meshing, again, for this would require significant defeaturing if I wanted to build a hex mesh in the traditional way. But again, for each of these components, I'm able to just build an individual kind of bounding box for each of these components and drop them in. And so again, meshing for this is a trivial process. It's also fully automatable. So as we start talking about something we haven't really talked about before, but as you start looking towards automating for optimization purposes, whether in tools like iSight or Dakota or other optimization frameworks, or even agentic modeling or agentic simulation workflows, the ability to automatically be able to generate meshes robustly is something that we're really excited about. Okay, so I'll just pop open my caliper simulation here. And again, just to give some idea, it took about 54 seconds to compute that trimmed mesh on this part, about 12 seconds to convert this to an IGA or an Abaqus simulation, and then the simulation took about 40 seconds to run, assuming that it took the same amount of time as we normally consume. So I'll now look at the results. This is one thing that I want to bring up that for those of you who are familiar with Abaqus CAE does not support visualizing user elements. So for now, one of the things we're doing is we're following the documentation, which encourages user elements to have a separate mesh that the results are mapped onto. So during the trim process, in fact, about half the time we spend in trimming right now is to produce this TET mesh on all of those trimmed elements, and we map the solutions onto those. We are working on some advanced capabilities to use VTK to provide a better and more efficient output, but that's still considered an alpha or pre-alpha functionality. And so here I am we're looking at the results again on this tetrahedral mesh. So it's really not exactly on the CAD in this case for the visualization purposes, but rather on this TET mesh approximation of the results. But you can make out that we have all of our fillets. They're all captured by this TET mesh. And then the other thing I want to show, let's actually go over to VTK. So here are then these results in VTK. We store out some data. We're working on building some plugins. VTK is the format behind the ParaView visualization tool. If you're familiar with that, that's what I'm showing here. And so again, I can show also in VTK, we could also get back our actual CAD feature lines. So this is something that, again, we are looking for our customers on this first release to start testing this capability out and providing feedback. And then I've also run the rotor assembly. So I wanted to show, there's a couple of things you'll notice that Abaqus, one of the things that we create for as part of the simulations, we do create surfaces of our boundary conditions as well as our contact surfaces. And you can actually view those in the standard output database that Abaqus exports. And so here I can look at contact pressures for my simulation. Here on the final time step, I can see that there is contact going on in my simulation, as well as I can look at the full field results where like our stresses and stuff are. And so then that's what we're looking at here. Again, looking at this in Abaqus CAE in the ODB file. And again, I also have this in VTK as well. The last thing, since we did show that we could define probes, here are the results from my probe. We store this during the run in a JSON file. So that's a human readable text format. It's also machine readable. There are Python modules for this. There are MATLAB capabilities to read JSON, Julia. I'm sure there's C++ as well. And so what this is telling me now is I can find the displacements at the location I cared about at the final time step for that caliper, as well as my stress values. I have plasticity, but that problem doesn't go plastic. But if I had plastic strain, I could also extract the plastic strain. We're working on a user manual where we even show how you can import these results back into Abaqus CAE to use the XY data objects and the XY data plotting in Abaqus CAE as well. And so that's another way that we integrate this technology, the Abaqus CAE. And I think with that, we're on to our Q&A, Matt, if there's nothing else.
All right. So a number of questions have come in. How can I start using IGA and validate with my use cases? Does this come pre-installed with any of the Abaqus versions? How does that all work? So I'll go ahead and answer that. So Coreform IGA for Abaqus is a separately licensed plugin, and that's available from Coreform and also from a growing number of Abaqus resellers. So if you purchase Abaqus through a reseller, go ahead and reach out to them to see if they carry it yet. If not, we can work with them to make it available. Otherwise, you're welcome to reach directly out to us at Coreform, and we'll be sending a follow-up email about how you can get in touch with us. The way that we find it best to proceed, because this is a new approach and we want to be respectful of your time, we'll work with you to identify a simple part that's of interest to you that we can run, share that with you, and then that can serve as kind of a reference for you as you then start to explore and validate this on your own models. Okay, let's see. Next question. Thanks so much for the demo on the presentation. Are we able to have different mesh sizes? Can some parts have a smaller or larger mesh size relative to other parts in the same model? Greg, do you want to answer that?
Yeah, the answer is absolutely. You can absolutely have different mesh sizes. In this case, just for simplicity, I use all of the same mesh size. But yeah, these meshes are independent of all of their neighboring meshes. So for example, this rotor, I could give this rotor a different size. I could give this a size of like 2.5, for instance. And have a finer size there. And if we go back to our assembly, we should now be able to clearly see that that mesh size is finer than its neighbors. So yep, absolutely can. The only limitation today that for those who followed IGA is that right now we only have a global mesh size per instance. Soon we'll have the adaptivity as well, so you can refine around local features.
Okay, great, thank you. Another question: how do the IGA results compare with a TET mesh? Why would I prefer IGA to a TET mesh?
So the answer is both TET meshes and IGA are Galerkin methods. And so they follow the exact same theory as far as mesh convergence as you get from Galerkin theory. So in principle, as you refine both a TET mesh and an IGA mesh, you should get the same answer. Where there's differences is that we live in this world of floating point representations. And so things like conditioning matter for numerical algorithms like Newton-Raphson iterations for nonlinear solvers, iterative solvers for the linear solve portion. So if you're doing like a Newton-Krylov sort of approach to get improved performance, conditioning of your linear systems matters. And what we have seen and shown time and again is that these IGA meshes have really good conditioning. And so we get good convergence for these nonlinear problems without having to do a lot of tweaks. We have a large database of complex CAD geometries that have been given to us by our partners and customers over the years. And we test those geometries both in our trimming approach as well as with a world-class commercial TET meshing routine. And we actually find that more of the geometries mesh with our trimming approach than with TET meshing, just due to some of like the dirty CAD that happens on very small features that can cause TET meshing routines to fail. That's certainly not. That's certainly something that other TET meshing routines might be able to address, but at least the commercial tools that we're using do fail to mesh them. So it gives you additional robustness on the meshing. It's also parallelized. So some geometries that are really complex might take a long time to TET mesh. And because we parallelize and scale well, we can actually mesh them faster. And then because of their good conditioning, they work then really well for these nonlinear problems. So I definitely would say that if you have satisfactory results today with TET meshes and TET meshing approaches, then Coreform IGA for Abaqus probably isn't the right tool for you. You should use whatever tools let you solve your problems, to the level of accuracy and with the level of workflow complexity as works for you. And but if you find that TET meshes for certain problems aren't working for you, then maybe give Coreform IGA for Abaqus a try.
The question, we use HyperMesh as a preprocessor to set up and run models. Can IGA be used as part of that process? I'll go ahead and answer that. So as we've mentioned, we really do view IGA as the future, the next generation of finite element analysis. And we're interested in integrating IGA into every workflow that we can. What we're showing today, Coreform IGA for Abaqus, is integrated into Abaqus CAE. So that is the commercial preprocessor available today. If you're interested in support for other preprocessors, we'd love to talk with you and see what we can do there. A similar question, my industry uses FEMAP with Nastran. Any plans to integrate with that software in the future? Again, same answer as before. We do want to integrate IGA with every workflow. This is the fourth solver that we've integrated IGA with, actually. We've integrated it with some government codes. We've created our own solver based on IGA. And so with any software that you're interested in integrating with, we would welcome those conversations, and we can identify what those opportunities are. Another question about software. Which Abaqus version is required for Coreform IGA? So we're grateful for the team at Dassault. They've been helpful and supportive in making this significant integration possible. What that also means is that you'll need to take full advantage of IGA and Abaqus. You'll want to always be on the very latest version of Abaqus, and so there's been some significant enhancements to what's available and accessible through IGA that will be released in the upcoming Abaqus Hotfix 3. That's what we're waiting for to officially commercially release the first version of Coreform IGA for Abaqus, and that should be within the next couple of weeks. Okay, more technical question. What spline methods are used for the continuity between the Bezier elements in our mesh? Are they NURBS, U-splines, T-splines? Do you want to go ahead and take that one, Greg?
Yeah, at least what we've shown here today, these are just tensor product B-splines. So they're not the rational B-splines. They're just regular polynomial B-splines. We do have the ability to build U-splines. We're still working with the Dassault team on getting some additional information about their meshing routine so that we can add body fit U-splines as well into the Abaqus CAE. And then our refinement approach is based on hierarchical B-splines. So yeah, that covers. I'd say that we definitely have plans for U-splines. In general, we don't have plans for T-splines. U-splines were developed to resolve issues with T-splines for analysis.
Another question. So my understanding in the past is that Coreform IGA has worked on both implicit and explicit methods. What's available now in Coreform IGA for Abaqus?
Because we use UEL mat, that is specifically limited to Abaqus standard. So there is a UEL, which is just you write a user element and you have to also write material models for them. And then there's UEL mat, where you don't have to write the material models. On the explicit side, there is a VUEL, so a user element for explicit, but there is no equivalent of the UEL mat over in explicit, which is why we've focused on implicit for now. We are considering developing a technical demo using VUEL. But what our customers have told us a lot is that they have a lot of material models already in Abaqus that they trust, and we want to be able to reuse those material models. And so if you are interested in explicit dynamics, IGA can definitely do explicit dynamics and can do it efficiently. And so we'd love to hear from you what your use case is so we can help build a case ourselves for doing that development work.
Yeah, and is a lot of these questions are hinting at there are rich frontiers that we can push on, and we are really welcoming conversations with Abacus users as we triage and identify which ones to prioritize. So again, we'll be sending out our contact information right after the webinar, and we welcome having ongoing conversations with you. Another kind of frontier question: can this approach be used for CFD or FSI? There have been thousands of research papers published on isogeometric analysis over the last 20 years, and a number of them have demonstrated significant improvements and applications of IGA to both CFD and FSI. What we're releasing today with Coreform IGA for Abaqus is just FEA. Nick says that he saw there was a webinar about Coreform Qubit, which is the Coreform's leading hex meshing software, and how that integrates with calculus. Is there any plugin or integration plan for Coreform IGA with calculus? And I think, again, the comment there, we're just announcing Coreform IGA for Abaqus. We'd welcome to be in contact with anyone about questions for integration with any other software. And there's a number of other questions that they're asking about that for different pieces of software. Okay, from Francisco, for the output, do you get the VTK regardless of the ODB mesh workflow? Do you want to answer that, Greg?
Yeah, so at least today, the database that we utilize for VTK, we do generate. What we showed right now is in VTK, we've got like a plugin that we use internally, and that's what we use. We add that plugin to ParaView, and then we are able to visualize the data from that. You might have seen it's a SQL database. At least today, the plan is that SQL database will always be produced. And then if you have the plugin, you could visualize it. At some point in the future, just to be fair for everyone's compute resources, we will likely give users the option to have that file or not have the ODB files. But today you just get it, yes. But you do need to talk to us about the plugin, and the plugin is definitely like pre-alpha, and so we welcome your patience with that.
Trying to understand, is Coreform IGA for Abaqus just a mesh generator? What about the different element types that Abaqus usually uses? What about shells? How should we think about that, Greg?
Let me answer the shells first. So this approach definitely is currently only for solids. We have shown in the past, one of our former employees did his PhD showing the extension of this to shells. What our customers have told us, though, is that they would prefer to not worry about taking a solid CAD model and trying to mid-surface it to the new shells on, especially with things like gigacasting coming in, where it then almost adds more complexity of having to now do shell to solid coupling. And so one of the things we've demonstrated is that when you use these higher order elements, you actually get really good results for thin walled parts in bending, even with less than one element through the thickness. So essentially become mesh independent very quickly. And we have verification problems where we show, for instance, having less than one element through the thickness and getting the analytic result for like beam bending cases. Not an approximation like you would traditionally with linear hexes or quadratic hexes, but the exact analytic results. And so we feel pretty confident about being able to use this solid approach for thin bodies. And then as far as formulations, you are right that there are different formulations that we still have to handle, specifically around incompressibility. You have to handle the incompressibility constraint. And we are developing incompressibility formulations that then you can select in that exact same dialogue that I was showing previously. In fact, I think I still have this up here. I'll even show like notionally where these are going. See, I switch over to the part here. Edit. And so under this, I can choose if I want to use like a different incompressibility formulation. It's like a selective integration, B bar, F bar, or some new formulations we've been developing. So yeah, absolutely can do incompressibility there. And we also have advanced quadrature schemes that we've demonstrated in the past that haven't yet made their way into this tool. But there is still a lot of capabilities and functionality there for users who need that.
If the mesh is created through a Boolean operation between the CAD and the IGA mesh, then wouldn't complex geometries or features cause mesh quality issues such as poor aspect ratios?
Yeah, the answer is yes. It actually causes a lot of issues. Even just doing the Boolean operations on the actual CAD geometry is really challenging. So we've actually worked closely with another Dassault subsidiary, Spatial, who develops the ACES kernel that's used by Abaqus CAE as well as our Coreform Qubit to improve the robustness of those Boolean operations. I think there's a white paper case study that you can find on Spatial's website. And so we've solved a lot of problems there in terms of just the actual Boolean operations. And then as far as the aspect ratios go, is that you are right, that those can lead to sliver elements, which would result in poor conditioning. And so that's where we spent a lot of the time, especially over the last 6 years, have been really developing salient approaches to addressing conditioning of those poorly formed trimmed elements to rectify them. And we've done a lot of work in that area. And so far, we're seeing that our approaches work really well.
Question from Daniel. Does the trimming algorithm for the mesh, does that work with any internal structures or does it just work with the outer surface?
Yeah, it works with internal structures as well. So just as an example, if I had, say, like a cube with a hole and a hole cavity or a spherical cavity on the inside, we would trim to that internal spherical cavity. So it's essentially just as a bounding surface of the CAD geometry, we trim to it.
Okay, another question, trying to understand the relative merits or the differences between IGA and TET meshing. So is it appropriate to understand that IGA has C1 continuity and TET meshing has C0 continuity? Is that accurate?
That is accurate, yes. And in fact, IGA, if we go to cubic bases, we can have C2 continuity. So we can always increase that continuity. And TET meshes are generally in the, I believe that there's some papers from Gilbert Strain from like the 70s that talked about how building smooth TET meshes requires like very high orders before you can start to get smoothness, and maybe even some special layouts that effectively are structured TET mesh layouts. So that means that effectively all TET meshes are C0, effectively, to my knowledge. And yeah, that's the benefit of IGA, is you can build smoothness into the basis.
So here's a question. What if the CAD is not exactly where it needs to be? After we create the IGA mesh, can we then move that to for contact interfaces or for appropriate clearances?
Yeah, so there are a few things you can do, but we do support like the like initial adjustment of meshes. So there's an option like in contact where you can adjust the mesh and to like ensure there's no overclosure. So that can happen automatically. We do create this input deck that then produces these surface meshes that I mentioned, which are, just to show these again, you go over to the visualization module. So again, the X's here, that's the default rendering of user elements in Abaqus. And those are these R node 3D. So if I remove those, you'll see that what we're left with are my connector elements and then these surface membrane elements. And so you'll find those surface membrane elements in the INP file that we star include. And so if you need to do some micro adjustment of those, you certainly can. It's probably a little bit more difficult to talk about what it means to deform the trimmed geometry, but we're definitely interested to talk to you about the kind of issues that you see there and how we can address those.
Greg, is it possible to implement element birth or death techniques for example, to model time-dependent domains?
Yeah, there's a difference between possible and implemented today. With IGA, you can definitely do birth and death routines. We've demonstrated it before for like projectile penetrator simulations, showing like element death. So you can definitely do it. We don't have that support today in the Coreform IGA for Abaqus. But again, we'd love to hear what your use case is and start talking about that. I actually personally think that we start talking about things like additive manufacturing and wanting to be able to add material. I personally think that IGA provides a really good framework for being able to do that in an efficient, robust, and accurate manner. But that's probably a topic for a later date.
Thanks again, everyone, for coming. And Greg, thanks for the great preparation for the webinar. We're eager to continue the conversation. If you're not connected with us on LinkedIn yet, follow Coreform, connect with Greg or myself. We'd love to talk there. Reach out to sales@coreform.com. Thanks again for the time for everyone, and have a great rest of your day.